Hey guys, welcome back to Comp 1113, Unit number 3, Floating Point. This is video number 1, where we'll be discussing IEEE floating point rules with regard to the single and double precision floating point data type. And we'll also dive into the special cases involved with those floating point numbers. Floating point representation is basically using scientific notation. So I thought we could first review a little bit about scientific notation in base 10 before we start going after binary scientific notation. What we're doing now is we're moving from our unsigned integers and our signed integers into a way to represent floating point numbers that, this will allow us to handle very large numbers and very small numbers. Here's a number on 8 bits. Depending on where the radix point is, it affects the size of the number significantly. Floating point will be recording this number using basically a scientific notation version of this. We'll be moving our radix point sort of the way we do in base 10, and then recording things like the exponent. Here's a very tiny number in base 10. It's an electron charge. If we were going to write that in scientific notation, as you recall, we would take the decimal point and we would move it to the right until we ended up with 1.6. So we keep track of how many times we had to move it, and each one of those is a power of 10. Because we're moving to the right, we're making our exponent will be negative, so our answer will be 1.602176 times 10 to the however many places we moved there, and it looks like we've gone 19 spots to the right. So I have trouble keeping track of should this be positive or negative sometimes, but it's pretty straightforward. I took this tiny number and then I made it bigger. So in order to keep it the same size, I guess I need to make the exponent, to the minus sign, or really small. The scientific notation is nice because it lets us store these really tiny and also very large numbers precisely. So here's a large number. When we're dealing with a large number, now we take our decimal point and we move it to the left. And we just keep track of how many spots we move it, and that's our power of 10. So in this case, I'm making the number smaller. I took this giant number, and now I'm writing it as 6.24151. So to balance that, I will have to raise it to a power that is positive. So we moved it 18 spots, so 10 to the 18th. This hopefully is familiar to most of us. Now we're going to take this same concept and apply it to binary numbers. When we have scientific notation, I guess there are a few key parts. We need to get some terminology here. We have the base, this is a base 10 number. We have the exponent. And then we have this other piece that will give it the name mantissa. And in order to record as much information as we can about this number, we would also need to know what the sign was. This is sort of your normal form. We'll call it normalized form for scientific notation. When you move that decimal point until you have 1 point something. And that's the way we normally do it. I know that some engineers will move it all the way so that it's always 0 point something. But I mean, that isn't what we consider the normalized scientific notation form. So scientific notation ends up being sort of a sign magnitude kind of representation. You have a separate piece for the sign, and then you need to store the mantissa, and you'll have to store the exponent. If you know those three pieces, you should be able to reproduce your number, provided you know what base you're in. Base 2 floating point will look similar. Our first step will be to take our number and convert it to binary. So here's a number, negative 219. We could store that in 2's complement, and it would be, great if we stored it that way. But perhaps we declared our data type to be float, and then the number negative 219 ended up getting assigned to, whatever variable we used. First things first, convert 219 to binary, divide by 2 over and over again. Look at your remainders in reverse. Here's negative 219. Now this is just regular binary. I haven't converted this to 2's complement or anything weird. Now we're going to take this form and do something different with it. We're going to take the radix point and we're going to move it just like we would if we were dealing with scientific notation in base 10. In this case, we're going to move it 7 spots. 1, 2, 3, 4, 5, 6, and 7. And we're moving it to the left. So we're making the number smaller, which means we have to balance that by making the exponent larger. Each move is a power of 2 instead of a power of 10. So the procedure is pretty natural. If you're used to regular base 10 scientific notation, this shouldn't seem too bad. The worst part is, I guess, the conversion to binary, perhaps. We have our mantissa, we have our sign, and we have our exponent. When we're dealing with binary numbers, that leading bit will always be a 0 or a 1. In base 10, actually, it should always be a 1, shouldn't it? We'll always just keep moving this decimal point until we get 1 point something. In base 10, we'll move it until this number is between 1 and 9, I guess. I shouldn't say always, but normally. So when we're in normalized form, that will be the case. Again, the number could be recreated if we know the sign, the mantissa, and the exponent. And we'll assume that we know what base we're working in at all times. To store these numbers in a computer, we have to come up with a standardized way to do it. So the International Electronic Engineers got together and sort of weighed the pros and cons and came up with a way to do floating point. And everyone has basically agreed to live by, these rules. Single precision floating point, we will use 32 bits to store our numbers. So we have our 32 memory locations, and now we're going to try to store the number that we had converted to scientific notation. To do so, we'll do something similar to what we had done before. We reserve the first bit of the 32 to be the sign. And we'll use a normal naming convention there, where if the sign is positive, we'll put a 0 in this spot. And if it's negative, we'll put a 1 in this first spot. Then, what might be a little weird, we store the exponent next. So we need to store this number 7 in some number of bits. So it was agreed upon that we would use 8 bits to store the exponent. So first you have the sign, and then the next 8 bits are the exponent. Now, we can't just put the number 7 in those 8 bits. We'll have to put that into some binary form. We could store it in 2's complement, for example, because sometimes this exponent is negative. So we need a representation that can handle both positives and negatives. It turns out we're going to end up using a biased representation rather than 2's complement because exponents generally involve incrementing. And we learned in the last video that bias and excess and bias are great when you have to do some sort of incrementing. The rest of these bits will be used to store the mantissa. When we stored the exponent, the rule will be bias 127. The mantissa will store that as many bits as we can of the number, and at some point we'll have to do a rounding or a truncation. When we're looking at this mantissa, if it's in normalized form, binary is interesting in that this first bit will always be a 1. In base 10, sometimes this is a 7, sometimes it's a 4, but in binary, because you only have 0s and 1s, you'll move that radix point until it's 1 point something. Therefore, since it's always a 1, we don't necessarily need to store this leading bit. We only need to store the fractional part here, the part to the right of the radix point. We'll call this the hidden bit then, where we will just assume that there's going to be one there at all times when it's normal. And then we only need to store the rest. So in this case, I don't store the hidden bit, but I store the remaining bits, and then I pad the rest of the memory with 0. We've now stored this number perfectly. We didn't have to cut anything off. We didn't have to make any rounding decisions. There were enough bits to store all these spots. Of course, sometimes when we're doing these problems, we would have to make a decision and either round it or truncate it. Double precision has a standard as well. Instead of doing 32 bits, which can store some pretty big numbers and some really tiny numbers, if we need to store even bigger than that, we'll go to 64 bits. Similar format for the memory. The first bit is a sign. Then we use 11 bits for the exponent. And then we have 52 bits left for the mantissa. They don't really fit on my PowerPoint screen, so I don't like to do very many double precision examples because 64 bits is, quite a string. The exponent on 11 bits is recorded in bias 1023. So we'll use bias 127 when we have single precision and bias 1023 when we're in double precision. Basically floats and doubles. This is, again, when we have the normalized form. We're going to run into a couple of special cases as we go along. Excuse me. So when we get to those, we'll cover the unnormalized form. But I made you a little summary chart here to help remind us, how the bits are divided up. When you have 32 bits, it goes 1, 8 for the exponent, and then 23 for the mantissa. And when you have double precision, you have 1 sign bit, 11 for the exponent, and then 52 for the mantissa. If it's in normalized form, you don't have to store that hidden bit because it's always a 1. Why might we choose the bias 127? Again, it's because the binary codes are in order, which makes incrementing easier. Normally for bias 127 on 8 bits, the range would go from minus 127 up to positive 128. So if I made a chart here, minus 127 up to positive 128 on 8 bits, I would have the strings, 8 zeros up to all ones. Well, the actual range of our exponents won't be quite so wide. We're going to reserve the all zeros as a special case, and we're going to reserve all ones for special cases, which means that instead of having a range of minus 127 up to 128, we'll actually cut one off of each end, and we'll only actually go from minus 126 up to positive 127. That's this point here. Whenever we see an exponent that's all zeros, that will be like a flag saying, hello, this is a special case. Do something else. Do something special. Same when we have exponent of all ones. So that reduces our range of exponents. We're just going to say we don't get to use negative 127 and we don't get to use positive 128 the way we normally would. So our actual range of exponents will be from minus 126 to positive 127. And I updated my chart here to reflect that. So these are our possible exponents then. In normalized form, we always have 1 point something. But that gets us into trouble, because what would you do with the number 0? When you have the number 0, how do you ever make that as 1 point anything? So the number 0 is one of the special cases that we need to be aware of. Basically, it makes a lot of sense. The number 0 in single precision standard will be the case where everything is 0. So that's a very logical code here. We could use some other code, but this one seems very appropriate for the number 0. We'll have to have a negative 0 as well because of that sign bit could be 0 or 1, which is a little bit of a waste as we learned when we were discussing integers. But because we have so many bits to work with, losing one of the permutations is not a big loss there. So here's a special case of the number 0 represented in floating point. We might run into a case where the numbers get so big that rather than giving an error, we might want to say, well, the number is so big, let's call it infinity. So to represent that, we'll use an exponent of all ones. That's a special case there. So whenever the exponent is all ones and everything else is a 0, then it's positive infinity. And we also can have negative infinity, a negative really large number. So those are, again, special cases. We basically just have to memorize these things. We have cases for things that aren't numbers at all. At some point during your calculation, you take the square root of negative 5. That isn't a real number, so you have to put something in memory. So you declare it as not a number, N-A-N. The code for that is all ones for the exponent. And then for infinity, we had all zeros in the mantissa, but for not a number, we just need a 1 somewhere in the mantissa. So it could be anywhere in there. As long as there's at least 1 1 in the mantissa, we have not a number. So there'll be lots of permutations for not a number. I guess we could have negative not a number as well. But because it's not a number, it seems weird to put a minus sign in front of it. So let's just also call that not a number. So these are our special cases. We had 0, we had positive and negative infinity. Now we've introduced not a number. There's still another special case that's we have to deal with, and this is called the unnormalized form. This allows us to store numbers that are really tiny, like tinier than what the tiniest thing that we thought we could store. On 8 bits in BIAS 127, we said the smallest number we were going to get down to was minus 126. So 2 to the minus 126 is the tiniest number. When it's normal, when it's a 1-point number. However, we could maybe go even smaller than that if we were allowed to have the number start with something other than 1. Like if we were allowed to start it as 0 point. We will represent that special case with all zeros in the exponent as well. So we had all zeros in the exponent when we had the number 0, but then the mantissa was all zeros as well. If the mantissa isn't all zeros, then we have this unnormalized form. And once we recognize that we have an unnormalized form, we'll write it as 0 point something rather than 1 point something. When we recover our hidden bit will be a 0 rather than a 1. We'll have to remember that in BIAS 127, even though the smallest number technically is negative 127, that the smallest exponent we're allowing is negative 126. We'll do a little example here. Here's a special case number. I know it's special case because my exponent is all zeros. The first thing I ask myself, is this 0? And the answer is no, because I found a 1 in the mantissa. So now I know it's in that unnormalized form. It's a positive unnormalized form. And because I know it's unnormalized, I know that it's going to be 0 point rather than 1 point. And instead of actually calculating what this exponent is, because all zeros is technically negative 127, I just have to remember that in the special case, the exponent is minus 126. So the number here is represented in this form. So technically, if we were going to try to normalize it, it would be 1 times 2 to the minus 130. But minus 130 doesn't fit in our 8 bits in the usual way. But in an unnormalized way, it does. I know that the wording here is frustrating in some ways. Unnormalized and normalized. So this is kind of neat that it allows us to store tiny numbers. The tiniest number I guess I could write here would be all zeros in the mantissa, and until the last bit here, put a 1. That would be the smallest, IEEE 32-bit number that I could store. So this one is small, but not the smallest. Here's another one. I look at this string of 32 bits, and the first thing I do is I put my eye on the exponent, and I see that it's a special case because it's all zeros in the exponent. Then I go, oh yeah, it's a negative 1. And then if any of these are a 1, I know it's unnormalized form. If all of the mantissa is 0, then this would have been negative 0. So I'm going to write this as 0 point the mantissa times 2 to the minus 126. So these are sort of weird that they have this form of having a 0 as the whole part. But this ends up allowing us to store really tiny numbers. And then there are very few errors when we define numbers in this way. You know, that is where problems can happen when you add a tiny number to another tiny number, or the real problem happens when you add a tiny number to a big number. Oftentimes the tiny number doesn't influence the big number enough, and then you haven't added anything at all. So by allowing us to store a lot of decimal places here, you know, it helps with those errors. We'll discuss these errors as we go along. It's actually really hard to show errors when you have 32 bits to store your number because it does such a good job. Single and double precision numbers are quite precise. So as an academic experience, we are going to invent our own floating point. At BCIT, we've invented a floating point number system. It's not a number system that's used anywhere. It's only used at, well, as far as I know, only used at BCIT. And we use it to show what can go wrong with floating point numbers. And that's what we'll do in our next video. In the next video, we'll introduce our BCIT floating point, and then we'll go through all the pitfalls that can happen with floating point. We'll discuss all these special cases again with, you know, the unnormalized form, infinity, 0, etc. We'll have all of those things also with our